Okay, this example looks very complicated, but it can actually be simplified into our category 2. It is simplified into a case that two parts bonded together and they will always have the same deformation. Okay, let's read this first. It's aluminum tube with a cross-section area of AS equals 600 is used as a sleeve for a steel boat having cross-section area of 400, and when the temperature is 15 degrees Celsius, the nut holds the assembly in a snug position such that the axial force in the boat is negligible. Okay, so in the beginning, no internal forces. If the temperature increased to 80 degrees Celsius, determine the force in the boat and the sleeve. Okay, so in this example, you can see that we didn't add any external force. It's only temperature change. Okay, we just heated it. Then some forces, some internal forces and stresses will be generated in both components. Right? And the material properties have been given. Just let's try to solve it. Okay, so as I mentioned, this belongs to our category 2, since the sleeve and the boat are tied together. So when you heat it, cool it, perhaps not cool it, when you heat it, both of them will be elongated. Then since the sleeve is aluminum, it has a larger thermal expansion coefficient, so it will tend to become larger. Then the steel boat, will not allow it to become larger than the steel boat, right? So the sleeve will be compressed and the boat will be stretched, right? So this is the basic analysis. You can also do another analysis. For example, if we cool this system, we cool it from 15 degrees Celsius to 0 degrees Celsius. You can try to do another analysis if any stresses will be generated in the system. Okay, this is your own work. Okay, I leave it to you for you to do this basic analysis for a cooling process. So in this example, let's just look at this heating process. As we just analyzed, when you heat it, both parts will tend to become larger. Right? They will be loaded in some way. Okay, we have 4 steps to solve these indeterminate problems. Right? The first step, as we just this is a basic review. Right? We just talked about these 4 steps. The first step will be free body diagram, right, to build equilibrium equations. Then the second step will be to define the deformation force relations. And the third step, based on the step 2, we will write the compatibility equation. Then to solve it. Okay. So if we couple thermal problem into an elastic problem, then the second step will be changed. Right? The second step will be changed because we have not only elastic behavior but also a thermal behavior. Right? So in this case, each of these 2 parts will have a elastic deformation and a thermal deformation. Elastic deformation can be determined from this basic equation, FL over EA. And the thermal deformation will be from alpha delta TL. Right? So the overall deformation will be elastic deformation plus thermal deformation. Right? Since these 2 parts are tied together, so we will write that the delta sleeve equals delta boat. Right? So this is our compatibility equation. Okay, this is the third step. Compatibility equation will be the same but each one of them will have two components. Right, this is elastic components of the sleeve plus thermal deformation of the sleeve, and this one also have two components: elastic of the bolt plus thermal of the bolt. Right. So each of them has two components. Okay, so you can see that we just need to modify actually the second step. Okay, so we can solve this problem. Let's just solve it step by step as we just analyzed. So the first step, free body diagram to derive the equilibrium equation. Right? So this will be a little bit tricky since we have these two things, no external load. How can we get the free body diagram? It will be the same, right? You just cut it from here to make it free, then add the internal forces outward, right? So let's draw it here. This is the bolt, and we have the sleeve. You see the red colored is the aluminum sleeve, and the blue colored is the steel bolt. Okay, we have cut it from here and get this. Then you can see, let's add the internal force FB to the bolt and internal force Fs, the internal force of the sleeve. Okay, both outward, right? So we add them both outward. No other external forces. Okay, so the equilibrium equation will be very simple. Right? That will be just FB plus Fs equals 0, right? Or negative FB minus Fs equals 0. Okay, this is our first equation, equilibrium equation, because we don't have any other external forces, only these two internal forces. Okay, so add them together, you get the first equation. Or you can write it in another form, just FB equals negative Fs. Okay, this is our equation 1. So second step, let's find the deformation component, the correlations between deformation and force and other driving forces like temperature change. Right? So here we just need to realize that both of them, both bolt and sleeve, have elastic and thermal deformations. So our delta B, the deformation of the bolt, will equals the delta B elastic plus delta B thermal. Right, delta B elastic can be solved from FB LB over EBAB plus alpha B delta T times LB. Right. Then in the same way, the delta sleeve equals delta sleeve elastic deformation plus delta sleeve thermal deformation. So here we will have Fs Ls over ESAS plus alpha S delta T Ls. Okay, we just got these correlations. Right? Just keep them in this form now. Let's look at the third step. Okay, third step is to write the compatibility equation. What is the compatibility equation here? Since they are tied together, right, they will always have the same deformation. So this will be delta bolt equals delta sleeve. Right. Okay, so from here, from these two equations, this one equals this one. Right. So we just write them together. So we will get FB LB over EB AB plus delta T alpha B LB equals FS LS over ES AS plus delta T alpha S LS. Okay, this equation looks very long, but you should have realized that in these equations we have a constant actually, right? That is L. Right? Because in this case, our L B equals what? Equals LS. Right? They have the same length. This is L B or LS. Right? They are equal to each other. You can see that in this equation we have 4 terms, and in each term we have a L, B, or LS. Right? So this L is gone. Right? After that, we can simplify this equation, and based on this, we can write, we can derive FB. Right? This FB equals what? Equals this part times times EBAB, right? So FB equals FS over ESAS plus delta T alpha S minus delta T alpha B times EBAB. All of these things are constant, right? All of these things are constant, constant, and these have all been given. Okay? All of these numbers have been given. Okay, we just have just 2 unknowns, FB and FS. Right? So from here, if you substitute the numbers in, substitute all numbers in, you will derive that FB equals 1.826 FS plus 57,200 Newton. So this is our equation 2. Okay, our equation 1 where is our equation 1 is here. Right. Equation 1 said FB equals negative FS. Okay, so our last step is to solve it. Right. So naturally here, since we have equation 1 much easier, so we just substitute equation 1 into equation 2. Right. So here we can get negative 2.826 FS equals 57,200 Newton. Okay, so FS equals negative 20,240 Newton, and FB that equals positive that, right? Since they just have an opposite sign, right? This is 20,240 Newton. Okay, so the rest of the work will be easy enough, right? Just calculate stresses. So the stress in the sleeve will be Fs over A. That is negative 33.73 MPa. And the stress in the bolt will be Fb over A. That will be a positive value. But since they have different cross-section area, right? So the stress value will not be the same. This is a positive 50.6 MPa.